All right, here we go with the second part of the final exam review. There's not many things left this whole semester, so just as a reminder of what's coming up, we have the third part of this will be tomorrow, 2 p.m. in SCC 102. So same as the normal exam review session. It shouldn't be nearly as long, so we'll only have about 10 or 11 problems to go over that day. And then after that, we just have one more homework assignment due Sunday. I'll do a review video for that Monday morning. And then the rest is just getting ready for the final exam. So office hours are posted in Blackboard if you want to come find me during the next week or so as you prepare for the exam or want to talk about your final grade after that. And then if you need to make an appointment with me, just please let me know. We can work out other times as well. All right, so without further ado, let's get into today's material. So the first question, we're on to sort of the second third of the course now, which would be chapters 4, 5, and 6, which was covered in the second exam. Speaking of exams, I did have one person ask what the average was on exam 3. I just had a chance to look at it right now, so I haven't gone through a full deep dive into it, but the average for exam 3 was almost identical to exam 2, a little bit higher. I think exam 2 was 11.3 or 11.4 out of 20. This time was 11.6, so it was a little bit higher. So typically we see that exams 2 and exam 3 are roughly the same, and then we don't see the final exam being too much different in terms of average either. So that's what we had, and if I have time, I'll send out more detailed statistics later, but that's the most important one, what the average was. All right, so let's get into the material then. So the first question deals with which of the following molecules are linear. So this is a sort of subset of the VSEPR approach that we learned for determining the shapes of molecules. And when you're doing problems like this, you should recognize, and it is helpful in a lot of different problems on this topic too, not just this one, that if you only have 3 atoms in the formula, which is true for all of these answer choices here, then your only choices are going to be linear or bent. And so this one's asking which of them are linear. The only other option for these would be bent because there's 3 atoms in the formula. So there's other shapes that we need to be aware of course, that'll come up in a lot of the problems, but for this one, there's only 2 options, linear and bent. And that's going to again come down to the number of lone pairs on the central atom for all of these, because they all have the same number of total atoms in the formula, but how many lone pairs the central atom has is going to dictate whether the molecule adopts a linear or a bent structure. So we can go through all of them. And so for CO2, this one we've seen many times, we probably don't even have to go through all the details, but CO2, when we draw the Lewis structure, would look like this. We need double bonds to complete the octet on the central atom, and then 2 lone pairs per each oxygen. Again, but the important point for whether or not it's going to be linear or bent is going to be what happens at the central atom here. When the central atom in this case does not have any lone pairs on it, so it's AX2, and so there's only 2 total electron groups. They want to be as far away from each other as possible, so they're going to adopt a linear geometry when there's no lone pairs on the central atom. Okay, so that one would be linear. H2O is another one that we've seen over and over again, so this one should not come as any surprise either. When we draw the Lewis structure for H2O, it's very simple. We just have single bonds to hydrogen and 2 lone pairs on oxygen. And so in this case, the notation in terms of AXE would be AX2E2. And so this is a situation where we have 4 total electron groups, 2 atoms and 2 lone pairs. And so then in that situation, we're going to have a tetrahedral arrangement of those 4 electron groups, which then leads to the angles between the atoms being about 109 degrees, which makes them bent. So there's different bent geometries that have slightly different bond angles, but if it's not linear, the only other option, as I said, is bent when there's 3 atoms in the formula. So this one would be an example of a bent molecule where the 4 electron groups take up a tetrahedral arrangement, and that leaves the angle between the hydrogen being less than 180, way less than 180, about 109. All right, xenon difluoride, XEF2, is probably the weirdest one in this bunch, the one that's the least common, I would say, in terms of its electron group arrangements and so on. So in this molecule here, what we have are, so xenon is a noble gas, so it would bring in 8 valence electrons. And then each fluorine brings in 7 valence electrons. So we have a total of 22 electrons in this structure. So we have to make sure we get the number of valence electrons right before we start this one. It's a little bit more complicated than the last one, so we'll go through it in more detail. And then when we draw this structure out, xenon difluoride, after completing the octets on fluorines, so we reviewed Lewis structures last time, so that's going to be important for this approach as well. But when we complete the octet on fluorine, that's 16 of our electrons, 2 octets. and that leaves still 6 more for the central atom. So in this case, the central atom is going to have 3 lone pairs. And this one maybe is probably the least obvious of them, as I said. So this one has an AX2E3 notation. 2 atoms bonded to xenon, all these are AX2 something, but this time 3 lone pairs on the central atom. And when we have 5 electron groups, remember they arrange themselves in a trigonal bipyramid. And in a trigonal bipyramidal electron group arrangement, all of the lone pairs go on the triangle. So this time, all 3 positions on the triangle are taken up by lone pairs, and that leaves the 2 fluorine atoms 180 degrees apart. So this is another one that gives us linear. All right, so that was probably the least obvious of them. So far we have CO2 and xenon difluoride being linear. And then if we go to SO2, we have 3 group 6 elements in this. So 6 electrons from oxygen, also 6 electrons from sulfur, 6 from each oxygen, gives us 18 total. So when you have 18 electrons and you draw it out, if we complete the octets on the oxygens first, which we always do, that gives us 16 of our 18, so 2 more go on the center atom. Now this one would need a double bond to complete the octet, but we don't have to worry about that for AXE notation, because all that matters is how many atoms and how many lone pairs are on the central atom. It doesn't matter whether they're singly, doubly, or triply bonded. So we can stop here. Again, the better Lewis structure would be something like this if we want to complete the octet. But either way, however we draw it, it comes out to AX2E. So with AX2E, the 3 electron groups, the 2 atoms in the lone pair, are going to occupy a trigonal plane, triangular arrangement, which means again that the atoms will be bent, this time closer to 120 degrees, but still far away from linear. So this would be another one that's bent. So of these answer choices, CO2 and xenon difluoride are bent, and that corresponds to choice B here in this multiple choice arrangement. So this covers, I think, all of the possibilities for AX2E whatever structure. So AX2E0 is linear, AX2E1 is bent, AX2E2 is bent, AX2E3 is linear, and that's all the possibilities we'll have for 3 atoms in the formula. But again, linear or bent are only 2 options in that case. So there are a lot of other shapes and geometries you need to be familiar with, but these will come up from time to time as well, and make sure we're able to do those as we did here. All right, any questions on this problem or this topic in general? All right, so that was a problem of VSEPR, and then another major topic we covered in chapter 4 of this course, which was part of the second exam, was polarity. And so once we know the shape of a molecule, we can pretty easily predict whether it's polar or not, again, determined by that AXE notation and by the shape that it adopts. So in this problem here, we're asking which of the following has the greatest dipole moment. And so if it has a dipole moment, that means it's polar. And in problems like this, we don't really have a good way of ranking polarities of individual molecules. I suppose in certain situations, if they're the same shape, you could figure out which one's more polar based on electronegativity difference, or if it's just 2 atoms bonded together, like we talked about last time, polarity is sort of related to electronegativity difference. But for molecules like this that have a central atom and multiple things bonded to it, we don't really have a good way of ranking polarity. So if it's asking for the greatest dipole moment, we just need to look for the one that is polar. If it's nonpolar, it would have 0 dipole moment. If it's polar, it has a non-zero dipole moment. And so that's the first thing to figure out before you start trying to compare one to another. Just figure out, is it polar or is it not? All right, so let's go through these answer choices quickly. So CCl4, we've seen a lot of molecules now that have carbon at the center, and those tend to have 4 bonds and 0 lone pairs, because carbon will complete its octet in that way. So CCl4 looks like this. No lone pairs on the central atom, just on the outer atoms. So again, in terms of AXE notation, if you like that, this is AX4. But regardless of what the precise name for the shape is, regardless of how many outer atoms it has, any of these structures that have 0 lone pairs on the central atom are going to be nonpolar as long as all the outer atoms are the same. So here is carbon bonded to 4 chlorines. No lone pairs on the central atom means it'll be nonpolar. That's going to be true whether it's AX2, AX3, AX4, AX5, AX6. No lone pairs on the central atom, all the same outer atom gives us a nonpolar arrangement. All right, and then PF5 we go to. And so again, we need to be able to draw Lewis structure, so I'm not going through all the details of that, but what we would come up with for PF5 is after we complete the octets on fluorines, we've used up all of our atoms, sorry, all of our electrons. So that means we no longer have any left over for the central atom. So this would be another structure that has no lone pairs on the central atom. It's AX5, 5 identical outer atoms, again means that it's nonpolar. All right, so again, we need to know what these geometries are called, and I can go through that if you need me to, but for this problem, it's not so important. We just, again, have to recognize whether it's polar or nonpolar. And for all the ones that have no lone pairs, you can automatically get that they're nonpolar. Now, the next one is the simplest of them. We don't even have to really draw this one out. If you have a diatomic molecule, 2 atoms only, then there's only 2 possibilities. If it's 2 different atoms, it's polar, because that means the 2 different atoms have different electronegativity values. Or if it's 2 of the same atom, then it's going to be nonpolar. So O2, 2 oxygen atoms bonding together, has to be nonpolar because the same electronegativity for both atoms in the structure, so there's no unbalance in the charge. The electrons are shared perfectly equally in that case. So that one we don't have to draw out. Of course it's going to be linear, and because it's 2 of the same atom, it has to be nonpolar. The next 2 answer choices are the ones that we have to think about a little bit more, because if we go to xenon tetrafluoride, this is another fluoride of xenon, rare example of a noble gas compound. And what we get for xenon tetrafluoride is, after completing the octet on the fluorine atoms, we still have 4 electrons left over. So we have to put 2 pairs on the central atom as well. So you get a pair there and a pair there. So this one comes out to AX4E2. And for the different structures we have that have 2 lone pairs, so that would be AX2E2, AX3E2, and AX4E2, 4 possibilities with 2 lone pairs in the structure, then the polarity is not as obvious. There's not really a simple rule for it, so you have to think about the structure in more detail. So for AX4E2, we have 6 electron groups that go in an octahedron. So that's going to be a square with a flagpole coming out above and below. And then what we do for the octahedral arrangement is, if we have 2 lone pairs, the lone pairs need to be as far apart from each other as possible because they repel most strongly. So as you recall, when we have 2 lone pairs, we put them opposite each other, and that leaves the atoms around the square like this. This is a square planar structure. And this is a structure that's nonpolar because the dipoles that go between xenon and fluorine cancel each other out in opposite directions. So you have those 2 canceling out, those 2 canceling out. It's almost like 2 linear molecules superimposed. And so this one's going to be nonpolar. So again, for the structures that have 2 electron pairs or 3 on the central atom, some are polar, some are nonpolar. There's not an easy rule for that. You have to sort of, again, think about the structure, remember each case individually. And then finally, the last one here, choice E, is NF3. So what we get for NF3, again, there's a pattern that nitrogen tends to follow, which is 3 bonds and 1 lone pair. And that's going to be followed here. We have lone pairs in all the outer atoms, of course, but then the central atom gets a single lone pair. And what's easy to remember for the context of polarity is that any of the structures that have 1 lone pair on the central atom have to be polar. So this one is definitely polar because it has a single lone pair on the central atom. In that case, it doesn't matter whether it's 3 identical atoms. It doesn't matter whether it's AX3E or AX whatever E. 1 lone pair on the central atom, that's definitely going to be polar. So we're looking for the one that has the greatest dipole moment. This is the only one that's polar. All the rest are nonpolar, meaning they have 0 dipole moment. So this one, regardless of what that dipole moment is, has to be the greatest of these because it's non-zero. So that's going to be the choice we pick there. So typically in problems like this, where we're looking for greatest dipole moment, especially if we're comparing molecules that have, more complex formulas that aren't just diatomic molecules, but have, in many cases, 5, 6, whatever atoms in the formula. In that case, again, you're typically going to just be looking at, is it polar or is it nonpolar? And that's going to be enough to answer the whole question like it was here. Okay, any questions on that? Yep.
So you said if a chemical compound has a lone pair on the central atom, it's polar?
If it has 1 lone pair, exactly. Yeah.
What about multiple?
So if it has multiple lone pairs, there's different possibilities. So what we get for multiple lone pairs, let me make sure I remember all of these. So if we have AX2E2, so another important thing to remember for these is that the bent molecules are polar, linear molecules are nonpolar if it's the same outer atom. So AX2E2, we said last problem was bent, so this one would be polar. If we go to AX3E2, this one's not as obvious, but this is a T-shape, and that's going to be polar as well. But then AX4E2 we had in this problem would be nonpolar. So again, for the 2 or 3 electron pairs in the central atom, there's some of each. So T-shape is polar, bent is polar, but then the other one, this one is nonpolar, as we said. And then the last one that has more than one lone pair in the central atom that's going to be somewhat encountered is AX2E3. We said in the last problem that was linear. Linear molecules would be nonpolar. All right, so again, for the previous problem we were asking if they were linear or bent, and we didn't ask about polarity in that problem, but if we had, the linear ones would be polar, the bent ones would be nonpolar. So again, that takes care of this one and this one. For T-shape and square planar, you also have to keep in mind that this one would be polar for T-shape, and then as you saw here, square planar is nonpolar. So there's some of each if there's more than one electron pair. But there's only a few that are kind of in that weird category, so not too bad to rationalize and remember. All right, other questions? Yeah, go ahead.
So, well, let's say now we had an empty right here. We don't have one more. Let's say we come back to the compound is AX2E2 or AX3E2 that like has more one third on the atom. So how do we know which one has the greatest atom?
So in that case, you wouldn't be able to really easily compare it. So in problems like this, if we're asking for greatest dipole moment, it's typically going to be enough to just figure out which one's polar and you're done. Only one of the answer choices will be polar is another way of saying that. There are cases where we would ask you to compare dipole moment, but that's going to be just for individual bonds. So if we do like, you know, HI, HBr, HCl, HF sort of comparison, where it's just diatomic molecules, in that case, the polarity is determined by electronegativity difference. And so for an individual bond or for a diatomic molecule that just has one bond in it, then you can compare dipole moment based on electronegativity difference, which was what we covered in chapter 3. But for more complex structures like this, we don't have a good way of ranking polarity. It's not just based on number of lone pairs or anything simple like that. And I suppose if you have the exact same shape, then the electronegativity difference will determine whether it's polar or not. So if you're comparing, you know, H2O versus H2S, both bent molecules, the electronegativity, and there's the exact same shape, exact same number of lone pairs, all that, then the one that has the greatest electronegativity difference would still be more polar. But for these, they're all different shapes, so even if some of them were, you know, if there was more than one polar choice and they weren't identical in shape, you couldn't easily predict which one was more or less polar. So you have to, you know, again, for most problems like this, for the vast majority, just figure out which one's polar and you're good to go. All right, anything else? All right, we'll move on then. Then the other major topic that chapter 4 covered was bonding in covalent molecules. And there are, again, 2 major approaches we took for bonding. The first that we learned, which is in some ways a little bit simpler but doesn't tell us as much information, was called the valence bond approach, where the key concept there was called hybridization. And this is the idea that the atomic orbitals on each atom, in particular the atoms that we would define as the central atoms, are going to mix together. S and P orbitals are going to mix together, and they're going to give new hybrid orbitals that arrange themselves in the correct shape and orientation to give these different AXE structures that we've talked about. So that's hybridization, is sort of the key part of valence bond approach. And then the other thing that we can do with that approach is predict which bonds are sigma bonds, which bonds are pi bonds. There's 2 major types of bonds in covalent molecules that's determined by whether the orbitals are aligned head-to-head or side-to-side, sigma being head-to-head, pi being side-to-side. So this question here asks about both of those topics. We're taking acetic acid, CH3COOH, and we want to know the hybridization of each carbon atom and how many sigma bonds are there total. All right, so first we have to get a reasonably good Lewis structure for these types of problems. Sometimes the Lewis structure will be given to you, but more often than not, you either have to complete it yourself or at least fill in some of the key missing details. So in CH3COH, the way that we would draw a Lewis structure for a compound like this that has more than one carbon atom is the atoms that are closest to that carbon are going to be bonded to it. So the first carbon is going to have 3 hydrogens on it. And then to connect the whole structure, we need a bond to the other carbon. There's 2 carbons in the structure. And then the part of this that's not as obvious is the COOH part. So what does that look like? So this is, again, acetic acid. The COOH, what it means is that we have an oxygen and an OH bonded to that carbon. So again, it's not the most obvious way of writing the structure, but that's what it's going to look like. So if you see COOH, make sure you put that in. But then we have to fill in the structure. And again, for filling in the structure, you could go through the process of counting all the valence electrons, making sure you complete the octet, making sure you're using the right number. That still works, but it gets a little bit more cumbersome when you have this many atoms in the formula. So for organic molecules like this, we follow some patterns that we talked about for the different elements in the structure. So these compounds are going to be made up typically of hydrogen, carbon, nitrogen, and oxygen being the major elements that are going to be in these. Hydrogen is just going to have one bond. As I mentioned when I introduced this, putting anything besides one bond on hydrogen is just a crushing blow to my soul, so please don't do it. One bond only for hydrogen, no lone pairs, no double bonds, nothing like that. But then the rest of these are going to follow different patterns where they're all going to want to complete their octets. So all these atoms, carbon, nitrogen, oxygen, those p block elements that we usually have in these, they want to have exactly 8 valence electrons around them, but they do that in different ways to minimize their formal charge. So carbon is going to tend to have 4 bonds to complete its octet with 0 lone pairs. There are rare exceptions to these, but they're not likely to come up, so you can use this pattern to help you save time. Nitrogen is going to have still 8 total electrons, but that's going to typically be done by having 3 bonds and 1 lone pair. So still a total of 8. Each bond is a pair, each lone pair is a pair, but it's a different arrangement. And then oxygen would be 2 of each. And then the other one that might come up infrequently in some of these would be if you have halogens, which I'll abbreviate as X. So fluorine, chlorine, bromine, if they're not the central atom in the structure, but one of the outer atoms, those would tend to have 1 bond and 3 lone pairs. So again, continuing the pattern as you go across. So still complete octets for all these, but different arrangements. So in this structure here, we have carbon and oxygen to worry about. So carbon should have 4 bonds, and this first one already does because it's already bonded to the 3 hydrogens and to the other carbon. So we stop there for the first carbon. But then if we look at the second carbon here, this carbon only has 3 bonds, and this oxygen here right now only has 1. So carbon should have 4 bonds, oxygen should have 2, so we can take care of that by putting a double bond between those 2. We don't want to put a double bond here because that would add a 5th bond to carbon. And a carbon with 5 bonds is called a Texas carbon, even though that sounds cool, that's not chemically reasonable. And so we're going to just put, it's a Texas carbon because everything's bigger in Texas. But anyway, we're going to put 2 lone pairs there to complete the octet and oxygen. And then this oxygen here already has 2 bonds, so we don't add any more bonds, but we need to add the 2 lone pairs. All right, so if we want to have a complete full Lewis structure for this molecule, this is what we come up with. And then from here, what's going to be left is to predict the hybridization on each carbon atom. So the hybridization is going to be determined by the total number of electron groups that are present on each carbon atom. So this carbon atom here is bonded to 4 different things. So when you hybridize on carbon, you have an s orbital and 3 p orbitals available for hybridization. This carbon is bonded to 4 different things, so it needs to hybridize all 4 of those orbitals. So I'll call this carbon A and this carbon B here. So for carbon A, it's going to be sp3. You need to hybridize the s orbital and all 3 p orbitals to make 4 bonds. For carbon B, though, in this case, it still has the same orbitals available, but carbon B, we'll notice, has only 1, 2, 3 things attached to it. It's bonded to 3 other atoms, not 4 in this case. 1 carbon and then 2 oxygen, a total of 3. So it will only hybridize 3 of its orbitals, the s orbital, and now just 2 of the p orbitals. So for carbon B, it's going to be sp2 hybridization.
Why is carbon B sp2 again while carbon A is sp?
So that's determined by how many electron groups are attached to each carbon. So carbon A is bonded to 4 things, 3 hydrogens in a carbon, has 4 bonds, so it needs to hybridize 4 orbitals. So it's all 4 of those, sp3. For carbon B, it's only bonded to 3 things. It's bonded to 1 carbon, it's bonded to 2 oxygens for a total of 3 things that it's bonded to, so it'll hybridize 3 orbitals, making sp2. And that's the pattern that's always going to be followed when you're predicting hybridization. So that's the hybridization for those 2 carbon atoms. And then the next question was, how many sigma bonds are there? So from the valence bond approach, if you have a single bond, that has to be sigma. If you have a double bond, that's going to be 1 of each. So for the 2 bonds and a double bond, it's going to be a sigma and a pi. And then for a triple bond, which is as high as you'll go, always 1 sigma bond and the rest pi, so this would be 1 sigma and 2 pi. So that's how you determine for each bond in the structure, is it sigma or pi? So most of the bonds in this structure are single bonds, so they're going to mostly be sigma. All of those are sigma bonds, those 4 bonds on carbon. And then if we go to the other ones here, this is our only double bond, so that's going to be 1 sigma and 1 pi. And this is going to be sigma and sigma. So in total we have 1, 2, 3, 4, 5, 6, 7 sigma bonds. Make sure I count that right. 4 here, 3 here. So 7 sigma bonds. So those are the 2 parts of the answer there. sp3 and sp2 for the 2 carbon atoms, 7 sigma bonds, and the only other bond is pi, 1 pi bond. And again, thinking about why, how does a pi bond form? Well, we notice for carbon B here, we saved one of the p orbitals, we didn't hybridize it, and so the pi bond is going to involve the p orbital from this carbon that's unhybridized overlapping with another unhybridized p orbital from the oxygen atom. So when you have sp2 or sp hybridization, you're going to have unhybridized p orbitals, and typically those unhybridized orbitals, if they are going to be involved in pi bonding, or they could possibly be empty altogether in some structures, but in this case they would be involved in pi bonding to make that 1 pi bond there. All right, so any questions on these topics? Valence bond theory, hybridization, anything related to that? Yep?
How do you know the carbon atom has sp orbitals available?
So that's because when you're in the 2p block of the periodic table, so remember, this all comes from the valence orbitals that are available for that particular atom. And when you go to the 2p block of the periodic table, which is where carbon is located, in that case, the valence orbitals are 2s and 2p, so you only have s and p orbitals available. Now, for some of the heavier elements, if they expand their octet, we also invoke d orbitals. We have sp3d and sp3d2. You can't have that for carbon, nitrogen, oxygen because they don't have accessible d orbitals. Now, the reality is the other atoms don't really use their d orbitals either. That's kind of a convenient lie that we tell you guys. But nonetheless, we invoke d orbital hybridization just to sort of help understand it. But that cannot happen at all for the 2p elements. They don't have accessible d orbitals, just s and p. In any case, whether there were d orbitals available or not, if you're only hybridizing 4 orbitals, it's always going to be sp3. Or if you're always only hybridizing 3 orbitals, it has to be sp2. You're not going to use the d orbitals unless you go beyond 4 orbitals for hybridization, which is what happens if you have expanded octets, 10 or 12 valence electrons around that atom. Okay, any other questions? Yeah?
So the answer is 3 sigma bonds?
7. 1, 2, 3, 4, 5, 6, 7. So 7 sigma bonds. Yeah? Pi bonds will just be 1. So the double bond here is 1 of each sigma and pi. So that's the only pi bond. Yeah. All right, we good? All right, the other major bonding theory that we covered was molecular orbital theory. So this one was a little bit more abstract and a little bit, harder to wrap our heads around necessarily, but there's sort of, again, a very straightforward approach we use for it, and it only applies to very select types of molecules, mainly the diatomics that we talked about would be the only ones where we really have to talk about molecular orbital theory. So in this one, we're using the MO theory to predict the bond order in the C2 2- anion. So the important thing for molecular orbital theory, whether we're predicting bond order or number of unpaired electrons, is first to arrange the molecular orbitals in the correct order. So again, the way that molecular orbital theory works is we take atomic orbitals on each atom that's bonded together. It's going to be just diatomic, as we said. And we mix those to make delocalized molecular orbitals. And when 2 atomic orbitals mix, they form a bonding orbital that's lower in energy, and that's going to sort of hold the nuclei together. And they form an anti-bonding orbital that's higher in energy, where if you populate that, you start to pull things apart and weaken the bond. So you're going to form all these molecular orbitals, and the most important thing is to know what order they come in so that you can fill them correctly with the number of electrons that you have. All right, so we have 2 possibilities you have to remember as well. So for the p block elements, it's sort of divided in half. The first half of the p block, p1, p2, p3 configurations, boron, carbon, nitrogen, and the second half have slightly different arrangements of their molecular orbitals. Now, for predicting bond order, it actually doesn't matter if you get this right, but for predicting unpaired electrons or making assessments about the types of bonds that you have, it is important that you get this order correct. All right, so for the first half of the p block, what we have at the bottom, we always have sigma and sigma star for the 2s orbitals. So we have 2s and 2p valence orbitals for these elements. And if we were going to the lower rows, 3s and 3p would sort of behave analogously, but you're going to form sigma and sigma star from the 2s orbitals. And then when the 2p orbitals mix together, as we've already talked about in the context of valence bond theory a little bit, they can form sigma bonds if it's 2p orbitals that are arranged head to head, or they can form pi bonds, pi bonding orbitals and anti-bonding orbitals if they're arranged side to side. So with the p orbitals, you get both possibilities, and the difference comes in the ordering of the bonding p orbitals. So for boron, carbon, and nitrogen, the pi 2p orbitals come first. So bonding always comes first, but in this case it's pi first and then sigma. And then at the top you have always the same, pi star and sigma star. So that's the ordering if you're making diatomic molecules with boron, carbon, and nitrogen. And then for the other half of the p block, again, almost identical. But the only difference here is in the 2p level, the sigma bonding orbital comes first and then pi. The reasons for that are fairly complicated, so we don't need to worry about them too much. It has to do with the ability of s and p orbitals to mix with each other, but nonetheless you have to remember that there is this switch. So it only switches those two orbitals, that's the only difference. So I'll put a little box around those so you can remember. It's these orbitals here, they have to remember the order that they come in. That's what's going to be different depending on what molecule you have. And as I said, that's going to be particularly important for predicting the number of unpaired electrons. It doesn't really change the bond order at any rate, but we should still be aware of it. All right, so then what we have to do is once we identify the correct ordering, we're going to use this one here because we're talking about a C2 2- anion, two carbons bonded together with a negative charge. We have to count the number of electrons, valence electrons only for these, of course, we're just using the valence orbitals. So carbon is a group 4 element, so carbon is going to have 4 valence electrons, 2s and then 2p electrons as well. So we have 4 valence electrons for each carbon. There's 2 of them in the structure. And then we have a negative 2 charge that adds 2 extra electrons. So this is going to have 10 total valence electrons in it for the C2 2- anion. We have to make sure we get the right number of valence electrons. And then we fill them into the orbitals, lowest energy to highest energy, just like we would fill atomic orbitals. We do the bottom ones first and then fill them up higher. And we follow Hund's rule where if we have two degenerate orbitals, we put 1 electron in each before we pair them up. So now we just fill these up with 10 electrons. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's going to be the correct electron configuration for C2 2-. And then to calculate the bond order, which I did not space my things out very well here, so this is going to be tricky. But anyway, the bond order is going to be 1/2 times the number of bonding electrons minus the number of anti-bonding electrons. All right, so bonding minus anti-bonding, if you can't read what I just wrote there, so I'm running out of room. So bonding electrons are going to be electrons that are in orbitals that don't have a star next to them. So that's going to be these two there, 2, 4, 6, 8. So 8 of our 10 electrons are in bonding orbitals, 2 in sigma 2s, 4 in pi 2p, 2 in sigma 2p. So a total of 8 of our 10 are in bonding orbitals, and if there's 8 in bonding orbitals, that means the other 2 have to be anti-bonding. That's going to be those 2 here in sigma star. So 1/2 times 8 minus 2 is 3. So the bond order here would be 3. It's a triple bond. That's the highest bond order you can get using this molecular orbital theory for diatomic molecules. And so A would be the correct answer. That's the bond order of 3 when you have 8 bonding electrons and 2 anti-bonding electrons. All right, so once you get the correct electron configuration, getting the bond order is just the difference between bonding and anti-bonding multiplied by 1/2. That'll give you the total number of net bonds that you have in that structure. All right, any questions on this one? Yeah. How did I get, sorry, 10 electrons? So that's coming from, so this is C2 2-, so we're counting valence electrons for this structure. Carbon is a group 4 element, so each carbon atom has 4 valence electrons, so 2 times 4 is 8, and then because there's a negative 2 charge overall, we add 2 more to make it 10. So it's just the same as counting valence electrons for any structure that we'd have. This would be diamagnetic because all the electrons are paired. So you have 10 electrons, but all of them are paired up in the same orbital as each other with another one, so that makes it diamagnetic, and there's no unpaired electrons. And there are some helpful shortcuts you can take as well that don't necessarily give you the answer, but at least help you make sure your answer is reasonable. So if you have even number of electrons, like we do here, you need to have a whole number bond order, and it's going to be either diamagnetic or paramagnetic. So you do have to draw it out to figure that out. There's no shortcut there, but it can be either one. If you have an odd number of electrons, so occasionally we will give you, diatomic molecules or anions that have an odd number of electrons, like NO, for example, or O2 with just a -1 charge. Anything that has an odd number of electrons, you're going to have a fractional bond order, which would be something 0.5 in this case. And then it's always going to be paramagnetic. If you have odd number of electrons, they can't all be paired up with each other. It's impossible, okay? So again, there's some helpful things you can remember and sort of some patterns you can recognize. A lot of, learning science, and this is going to be particularly true as you go to more advanced courses like organic chemistry, a lot of it is about recognizing patterns. Knowing how to do the problem, of course, is important, but recognizing patterns can help you get there. And so these are some patterns that are helpful from like an orbital theory. If you have an even number of electrons, your bond order has to be whole numbers, so we can already eliminate 2 of the answer choices right off the bat. But it could be a paramagnetic or diamagnetic, so if we ask you about that, there's no shortcut to get there. For odd number of electrons, fractional bond orders only, so it can't be a whole number, and it has to be paramagnetic. So if we ask about magnetism for that, it's simple, you don't even have to draw it out. Okay? So any questions on those topics? Any more questions? All right, so then we're on now to the Chapter 5 material, if you're keeping track of where we are in the course, which deals a lot with moles, stoichiometry, things like that. The very first topic we introduced was the definition of atomic mass. So when you look up an atomic mass on the periodic table, which as we know now has significance in terms of telling you the number of grams of that element in 1 mole, what it tells us, the first problem here deals with the definition of that. So that atomic mass that you get, which we're giving you here is 107.87 for silver, that would be what you look up in the periodic table, is a weighted average of the isotope masses. So what we're telling you here is that naturally occurring silver has 2 isotopes, 107 silver that has this specific atomic mass, and 109 silver which has that specific atomic mass. You'll notice that the atomic masses of the isotopes are close to but not exactly equal to the mass number. So if we give you those specific atomic masses, those are the numbers you need to use. And if we want to know, and we tell you that the atomic mass of silver is 107.87, what is the percent abundance of the 107 isotope? And then this is a numerical question where you'd ask for your answer in 2 decimal points. So in problems like these that deal with the definition of atomic mass, that deal with mixtures of isotopes and the atomic mass that results from them, it all boils down to one sort of definition, one simple equation. So as we said, the atomic mass is the weighted average of the isotope masses, which is going to be given as the fractional abundance of each isotope. So in this case, we have 2 isotopes, 107 silver and 109. So it's going to be the fraction of each times the mass. And you just add it up for however many isotopes you have. In this case, only 2 of them. All right, so it's fraction of each times the mass. And so we have 2 unknowns here. Just to make the algebra a little bit simple, I'll call them x and y. So the fractional abundance of each I'm going to denote with the variable x and y, because that's what we're going to end up solving for. Fraction is going to be percent divided by 100. So if we want to get the percentage, we have to multiply by 100 at the end. We'll get there later. But that's going to be one equation. So if we write that in terms of x and y, the atomic mass of silver is given as 107.87, or you can look that up in the periodic table. And that's equal to, That's one way to walk down the hallway. Okay, so then, so we have, this is the atomic mass of silver, and we're going to have the mass of each isotope multiplied by the fraction. So it's going to be X times the atomic mass of the 107 isotope, which is 106.905, plus the second isotope abundance, which is Y, multiplied by the mass of that one. All right, I think he left. Good. All right, so that's going to be one equation that deals with, again, the definition of atomic mass. The atomic mass is equal to the fraction times the mass. But that's two variables, so we need the second one. We have to also remember, in a lot of problems like this, that the sum of the fractional abundances equals 1. So a fraction is just the portion out of 1 that would make up that element. So it's going to be, this is our second equation here, x plus y equals 1. In this problem here, we're solving for the fraction, or the percent of 107, so we're going to need to get x initially. So we can rewrite y as 1 minus x. Then we're going to substitute that in for y. Okay? So that gives us a new equation that's just in terms of x, where 107.87 is equal to x times 106.905 plus 1 minus x times the second mass, which is 108.905. All right, and then it just becomes a simpler algebra problem, so I'm not going to go through all the steps, but there's only a couple more steps left to get this. So x, again, is going to represent the fractional abundance of 107 isotope. And it comes out to 0.5175. Now, a common mistake that people make in problems that deal with fractions and percentages, so we talked about mass fraction and mass percent. This is sort of percent and fraction abundance for an isotope. Remember that percent is out of 100, so if you have to get to the percentage, you have to multiply that by 100. So we have to take the fraction and multiply it by 100 to make it a percentage, and it's going to be 51.75 as a percentage. So this element here, silver, is roughly composed of equal amounts of the two isotopes. It's only a little bit higher for this one, because the other one would, of course, be just the rest of the 100%, which would be 49.25, so pretty much equal amounts of both isotopes. And what you'll see is that the atomic mass is pretty much directly in between the two isotope masses, which is another way of telling you that. All right, but there again, this is the sort of first topic we covered in Chapter 5, and it does deal with the definition of atomic mass, and there could be problems on the exam that cover this as well. So any questions on that? All right. Yeah, so in problems like this is your main equation. It's just a function of what you're solving for, essentially, to get the answer. All right, so if we're good on that one, so I left a reminder here to take a break for course evaluations. There's not too many of you here, but I did promise that I'll give you guys time in class to do this. If you don't have, just to encourage some people to do it. I'm guessing the people that show up for class regularly are the ones that also do the course evaluations, so this might be a waste of time, but nonetheless, we get a 10-minute break either way, and we have plenty of time for that. So I'm going to pause the video so that the people watching online don't hear my heavy mouth breathing as I nervously wait for you to complete the evaluations. Okay, we're back from our little break where we did have some students doing evaluations during that time, so I certainly appreciate that. And we're going to get going on with the second half of today's review. So I divided it in exactly half. So there's our break is over, and now it's time to go into the second half of this. All right, so we're getting now into the part of Chapter 5 that deals with mole conversions and things of that sort. And so that's what this problem is going to deal with here. So we want to know how many phosphorus atoms are found in 5.00 grams of calcium phosphate. And so in a problem like this, we're giving you a mass of a compound, and we're asking for number of atoms. So we should immediately think of, we need to go through moles at some level. And so to get mass to moles, we do need to figure out the molar mass of the compound. And we didn't give you the formula exactly, so first you have to get the formula, and then you can get the molar mass. So for calcium phosphate, we have to make sure we know the formula of that compound. So calcium is a group 2 alkali earth ion, so it's going to have a 2+ charge when it makes an ionic compound. So that's going to be the charge on the metal. So this is an ionic compound, so we have to figure out the formula based on the charges of the ion. So calcium 2+, and then phosphate is the anion, and we have to remember that that's one of our polyatomics that has a formula of PO4 3-. So to get the formula for this compound, we cross the charges and make them the subscripts. That's the sort of easy way to do it. And what we end up with is Ca3PO4 2. So this ionic compound has 3 calcium ions and 2 phosphates to totally balance the charge. It'd be +6 from the metal, -6 from the anion. All right, so that's going to be the formula of the compound. And then what we need for this problem also is the molar mass, which was not given here. So as a review of how to calculate molar mass, which is often abbreviated as molecular weight, MW, it's just going to be the sum of the atomic masses. So we have 3 calciums, and the atomic mass of calcium is the number below it on the periodic table, which is 40.08 for calcium. All right, so 3 times 40.08 for calcium. Then we have to make sure we're counting the other elements correctly. So we have 2 total phosphates, PO4 taken twice. That means we're going to have 2 phosphorus atoms in the formula overall. So we're going to multiply the atomic mass of phosphorus by 2. Phosphorus is 30.97. Again, it's the number directly below it on the periodic table. So 2 times 30.97 for phosphorus. And then for oxygen, again, we have to make sure we're counting it correctly. So each phosphate has 4, but there's 2 phosphates in the formula, so 4 times 2 is 8 oxygen atoms. And that's an atomic mass we've seen all the time, which is exactly 16, so I won't flip back to the periodic table, but that's off there as well. So those are going to be the atomic masses we add up to get the formula mass or molecular weight of this compound, which is 310.18 grams per mole. So if we don't give you the molar masses, you have to be able to quickly and efficiently calculate them. So that's a review of how we do that. And then from there, we can approach the problem in just a string of conversions. So what we're looking for, again, when we're doing conversion type problems, especially those that involve moles, it's helpful to write down what you're looking for first, which is number of phosphorus atoms. And then you write the starting quantity as your first part of that calculation. So we have 5 grams of this compound, which we now know has a formula of Ca3PO4 2. And then we're going to calculate the number of moles of that compound using its molar mass. When you get to the middle part of this exam that deals with Chapter 5, Chapter 6 stuff, as we always talked about, whenever you have any doubts about what to do next, just calculate moles. That'll often get you where you're going. So that's going to be true here. We calculate moles first. That's per gram. That's 318 grams in 1 mole. So grams cancels out, and that gives us into moles of that compound. Now from here, there's sort of 2 ways we can approach. It'll be mathematically equivalent, but just 2 different ways of thinking about it. We can either calculate how many formula units of this compound we have by using Avogadro's number, or we can go into moles of phosphorus first, which I think for me is a little bit straightforward way to think about it. So from this, we have moles of compound. Now let's calculate how many moles of phosphorus are in that compound. And that's going to come from the chemical formula. So as we talked about when calculating the molar mass, there are 2 phosphorus atoms in the formula of this compound, phosphate taken twice, so there's 2 total phosphoruses, and that's going to then lead you with 2 moles of phosphorus for every 1 mole of compound. So these chemical subscripts can be thought of as in terms of individual atoms in 1 molecule or 1 unit, or in terms of moles. So if you have 1 mole of this compound, there's going to be 2 moles of phosphorus. That gets us into moles of phosphorus. But again, we're looking for how many phosphorus atoms there are, not how many moles of phosphorus there are. So there's one last step, which is just the definition of a mole. 1 mole of phosphorus is going to have Avogadro's number phosphorus atoms. So we're going to multiply by Avogadro's number to convert moles into number of atoms. These last 2 steps you could have done numerically in either order. They would have just been labeled slightly differently, but would give you the same answer. So that's how many phosphorus atoms there are. We get 1.94 times 10 to the 22, assuming I didn't screw up any of the math. That's how many phosphorus atoms there are. And then this is one of those problems that we sometimes see in Blackboard where it asks for the log of the answer, which is just for reporting purposes. Doesn't really have any special meaning. But we take the log of that number. We can also accept exponential answers on Blackboard now as well. So make sure you just read the format that the problem is asking for and enter that in. But in this case, it's going to be 22.29 as a log. Or if you just enter the answer, it would just be that number there, usually in exponential notation as it's designated. So read the problem closely to see what format it wants you in. Here, it just wanted the log of the answer.
Well, this type of question, like where to take the logarithm of the answer before to this point, would that be on our test, our final exam?
It could be. So we're starting to phase those out. This is sort of a holdover from Blackboard of many years ago, which didn't really accept exponential answers very well. So that's why I always had you guys take the log of it. So you can just type in a number. We have been phasing those out in favor of questions that ask for the answer sort of in this notation. It would be like 1.94 E22 would be the way you'd more commonly answer it now. So again, just look at the problem. It'll tell you exactly how to enter your answer. If it's not a multiple choice question, if it's a numerical question. So just follow the directions closely and you'll be fine. All right, any other questions? Yeah.
It's P, like P4.
Well, phosphate is PO4. So the phosphorus atom is part of that polyatomic ion. And so since there's two of those ions in the formula, each ion has one phosphorus as a total of two phosphoruses in the formula, which is why it's 2 moles of phosphorus per mole of compound. So phosphate is the whole polyatomic ion, which is PO4, that has 1 phosphorus and 4 oxygens. That was important for getting the molar mass correct, because if you didn't have the right formula, you wouldn't get the right molar mass. In terms of calculating the final answer, again, the relationship just involving phosphorus by itself was what we needed, because that's what we're looking for. Okay, other questions on that? All right, and then the next one is another problem that deals with mole conversions. It's an unknown element problem, which we've had a few different flavors of throughout this course. And typically when you're trying to identify an unknown element, or in many cases an unknown compound, what you want to be able to do is find the atomic mass, or in the case of a compound, the molar mass of that compound. So here what we have is, we have a metal chloride that has the formula MCl3. So that tells us that whatever the metal is paired with 3 chlorides as the counter ion. And it contains 35.62% chlorine by mass. We want to know what is the identity of the metal. So in problems like this that ask you to identify an unknown metal, the way we're going to do that is we're going to figure out the atomic mass of the metal and then use the periodic table to figure out which element has the atomic mass that's closest to that. So whenever you're trying to find an atomic mass, or more generally a molar mass, remember the definition of it. The atomic mass, or one interpretation of it, is going to be the grams of that substance in 1 mole of that substance. So to find atomic mass, what you need are the grams of what you're looking for, in this case the unknown metal, divided by the moles of that. So we need those two quantities there to be able to calculate the atomic mass. Now, as a hint on this problem, it wouldn't be clear from just reading the problem, of course, but if anybody remembers what my favorite element is, that's going to be the answer here. But we'll see if that comes out as true or not. So how well do you pay attention in class? Do you remember what my favorite element? Anybody? Nope? Okay, so not almost. We'll get there. Almost. All right, we're done guessing. So, all right, so we'll get to the final answer, and it will be what my favorite element is, which I should have mentioned at some point. Maybe I didn't, but in this semester, but I usually do because it's hard to not brag about your favorite. Okay, so so here we're going to go through the process of finding this, though, because obviously you wouldn't know that if you're just reading the problem as given. So to find the mass of the element, we're going to assume that we have 100 grams of compound because we gave you a mass percent. And so if you assume 100 grams of the compound, then the masses of each element are going to be given by their mass percent values. So in 100 grams of compound, we know that the mass percent of chlorine is 35.62, so that tells us we have 35.62 grams of chlorine, and the rest would have to be the metal that makes up that formula. So 100 minus 35.62 would be 64.38. So we just subtract from 100 to get the mass of metal that will be present in 100 grams of compound. Because again, mass percentages tell you grams out of 100. So in 100 grams, this is how much chlorine we have, this is how much metal we have. So that's going to be the numerator when we calculate the atomic mass of our unknown metal. We could calculate the atomic mass of chlorine as well, but we don't need it, of course, because it's a known element, so we can just look it up. And then to find the moles of metal, this is where we have to do some mole conversions, kind of similar to what we did in the last problem. So what we're going to start with is we know how much chlorine we have, and we know the identity of chlorine, so we can figure out the moles of chlorine that correspond to that first. So we're going to take the mass of chlorine and convert it to moles using its atomic mass, which we would look up as on the periodic table as 35.45. So that's moles of chlorine. And then the other thing we know from the chemical formula, similar to an argument we made in the last problem, is that for every 3 moles of chlorine, there's 1 mole of metal in that formula. So the MCl3 tells us that that's the ratio in terms of moles of each of those elements in the formula. So we're going to use that relationship to figure out how many moles of metal we have. So moles of M over moles of chlorine. The chemical formula MCl3 tells us that for every 1 mole of M, there's 3 moles of Cl. So we can use that as a conversion factor to now figure out how many moles of M there are in that 100 grams of compound. So that comes out to 0.3349. So we're going to put that up here in the denominator to calculate atomic mass. So that's going to be grams per mole when we divide those two. And it comes out to 192.2. So then what we would do is go to the periodic table and figure out which element matches that atomic mass closest. So the atomic masses generally increase as we go through the periodic table. When we find here at IR, which is iridium, is 192.22 grams per mole. All right, so that's going to be the answer here. The metal in this formula would be iridium IR. And as I may have mentioned in this course, or certainly have before, that's my favorite element on the whole periodic table, so there you go. But again, the process for solving the problem is going to be this procedure here.
Why is iridium your favorite?
So that's an involved question. I don't know how, do you have about 30 minutes? No. It's, in short, it's because it's a metal that I've done a lot of research on, and compounds made of iridium often have very brilliant and very colorful luminescence property. That's what we study a lot. And it's just a really cool element to work with. So it's based on a long history with that and stuff I've been doing since graduate school, really. So it's a fun element. And it's used in cell phones and TVs, by the way, so you might have some if you have an OLED phone or OLED TV. Iridium would be one of the metals that's in there making the brilliant colors that you see, in combination with other things, of course, but that's what it's used for commercially. All right, any other questions? Yes? Second favorite, I might go with gold. I've had a good history with gold in my not just because of, I mean, I don't really care about jewelry and stuff like that, but the chemistry of gold is very interesting too. That was a big part of what I studied in grad school as well. So gold is probably my second favorite. So whoever gets gold, you were close, but not quite. Yeah, all right. Any other questions? Not related to my personal preferences, but to topics at hand, ideally. All right, let's go on then to 21. We just got a few more left to cover what we're planning for today. All right, so now we're on to, if you're keeping track at home again, we're at chapter 6 material now, talking about aqueous chemical reactions, aqueous chemical equations. So the net ionic equation for the reaction of sodium hydroxide and iron 2 chloride in aqueous solution contains which of the following species? So what we have to do for this is we have to balance the net ionic equation and then figure out which of these with the correct coefficient, the correct state of matter, correct formula, all that appears exactly as written in that balanced equation. So for net ionic equations, there's not really an easy shortcut to get there. We start with the total ionic equation, which requires us to, first of all, figure out what the formulas are of the two reactants, and then figure out how they're going to react with each other based on what we know about aqueous chemical reactions. So sodium hydroxide is going to be sodium plus with OH minus, that's just NaOH. And then iron 2 chloride. Iron is Fe, the 2 tells us that it's a +2 charge, and then chloride, as we should know by now, is Cl minus. It's in the 7th column of the periodic table, so it forms -1 anions. So the formula for iron 2 chloride would be FeCl2. So we have to make sure we get the formulas correct for problems like this. And so then what we have is 2 ionic compounds, sodium hydroxide and iron chloride, reacting with each other. So the only type of reaction that we really talked about that involves 2 ionic compounds reacting, where we could easily predict the outcome, would be a precipitation reaction. So what we do in that case is we swap the cations and the anions. The cation from the first ionic compound pairs up with the anion from the second. So sodium and chloride are going to combine to make sodium chloride NaCl. And then the second product is going to be the cation from the second reactant, which is iron 2 plus, pairing up with hydroxide, which is OH minus. So the correct formula for that would be FeOH2. All right, so those are the reactants and products. The reactants, we're talking about aqueous reactions here, so the two reactants are always going to have AQ next to them. indicating that they are initially dissolved in water. And then on the product side, we have two things left to do. We have to put coefficients in on either side to balance it, and we have to predict, are the products going to remain in solution, are they soluble, or are they going to form a precipitate, meaning they're insoluble. All right, so for these two, we have NaCl and iron hydroxide. All sodium salts, no matter what the anion is, if it's sodium plus is in the formula, that will have to be soluble. So that's going to be aqueous. And of course, we all know that sodium chloride is soluble. It's what we call salt more conventionally. And then the other product is iron hydroxide. Now we have to decide in this case, is this going to be soluble or insoluble? So hydroxide is one of those anions where most of its ionic compounds are insoluble. The exceptions are in group 1A. All the group 1A cations, lithium, sodium, potassium, are always soluble. And then there's a few group 2 exceptions. So the heavier group 2 hydroxides, calcium, strontium, barium. But anyway, all transition metal hydroxides, which is this is one of them, iron, are going to be insoluble. And so this is going to be the one that forms a precipitate in this case. So you have to remember solubility rules to be able to predict that, but hydroxides are usually insoluble unless they're paired with group 1 or group 2 cations. And that leaves then all we have to do is put coefficients in to balance this total equation here. So we have 2 chlorides on the reactant side, so we need to have a 2 in front of there. That leaves us with 2 sodiums and 2 hydroxides, so we need a 2 there to balance. So again, balancing precipitation reactions usually involves pretty small coefficients, and that's all we have here is a 2 there, 1 on each side. All right, so that's going to be what we call the molecular or the formula equation. That's where we leave all of the reactants and products intact. What we're looking for here is the net ionic equation. So that requires us to separate aqueous reactants and products into their ions and then cancel out the ones that are on both sides, which we call spectator ions. So then from there, we're going to produce what's called the total ionic equation, where we separate the aqueous reactants and products, but we don't get rid of anything just yet. So in the total ionic equation, everything that has an AQ next to it is going to be split up into ions. So NaOH is going to be split up into Na plus and OH minus, so it'll be 2 Na plus and 2 OH minuses. And then the second one, which is iron chloride, is also aqueous, so that's going to be the Fe2 plus cation. We're just separating it out into the cations and anions that make it up. And this is going to be chloride ions, but the subscript tells us that there's 2 chlorides in that compound, so we're going to make 2 Cl minuses when we dissolve that. And then on the product side, again, the ones that are AQ, aqueous, are going to be split up. So our sodium chloride is going to be separated into Na plus and Cl minus, each with a coefficient of 2 because of the coefficient in the balance equation. But then the second product, as we said, is insoluble, so that's not going to be separated as a aqueous species. It's going to be just left as FeOH2 solid. So that's total ionic, and then to get the net ionic equation, we have to get rid of those that are called spectator ions. Those are the ones that appear on both sides. So we have 2 Na plus on both sides, so those get removed as spectator ions. And we have 2 Cl minuses on both sides, so those get removed. So in a precipitation reaction, what's left for the net ionic equation are the 2 ions that combine to make your precipitate are going to show up in the net ionic equation. Typically, we write cations first and then anions, although it doesn't necessarily have to be that way. So we would write Fe2 plus and then 2 OH minuses combining to make insoluble iron hydroxide. That's the net ionic equation here. So then we have to ask ourselves which of these are appearing to answer this question. Which of those are in the net ionic equation? So sodium chloride does not form a precipitate, so we wouldn't see that. Sodium plus is a spectator ion, so as we said, that gets removed when we make the net ionic equation, so that's out. But then 2 OH minus, we see 2 OH minus there on the reactant side. And then FeOH2 solid, we see that on the product side of our net ionic, so 2 of those, C and D, both appear in the net ionic equation. So when you're approaching questions like this to ask what is in the net ionic equation, you have to again focus on the chemical formula, the state of matter, is it aqueous, solid, or otherwise, and the coefficient. All of those have to be true for you to select it as one of the answer choices. But both C and D appear in exactly that form in the net ionic equation that we generated. All right, so any questions on precipitation or net ionics or things like that? Yeah? A species is just a way of saying reactant or product, or substance is maybe more general way of saying it.
So So if this is like major species, is that the ones that aren't the spectator ions?
Well, I don't think we would use the term major species in this context. Major species would mean, what's the majority of if it's a mixture, like what's the majority of the mixture. But in the context of a reaction, a species is just a reactant or a product. And there's not really anything such thing as a major or minor species in that context. Any other, yeah?
So we have to know like the solubility.
Yes, so solubility rules could come up in questions like this where we ask you to predict whether something will precipitate or not, and that's going to be particularly relevant when we talk about these types of reactions where you're reacting two ionic compounds with each other, exchanging the ions, and often forming one or sometimes in rare cases two insoluble products. Another question in the back I saw? Yeah.
So for precipitation reactions, do they always occur as a double replacement?
Yeah, so it would be another way of terming that, which I don't know if our book uses that term or not, but I didn't. It's called a double replacement, where you would have both cations and anions swapping with each other. There's another class of reaction called a single displacement. That's a type of redox equation, which we didn't really cover in those terminology here. So these would all be classified as double replacement, where each cation and anion swaps with each other. You don't have to worry about that terminology, though. All right, anything else? Yeah?
So it's a precipitate reaction.
Yeah, it's a precipitation reaction. It forms an insoluble product.
And the ones you cancel, those are the
Spectator ions. Yeah. All right. How are we doing on time? Oh gosh, we're out of time. Crap. All right, we might fall one short today. I guess I was more talkative today. Spending too much time talking about my favorite elements. All right, so we'll do this as our last question. That's going to require us to do one more tomorrow than we were planning, but that's okay. We have plenty of time tomorrow to get through the last few. So we'll just finish with this one, which shouldn't be too bad. So we want to calculate the molarity of perchlorate in a solution containing 3.58 grams of aluminum chlorate dissolved in 125 milliliters of solution. So the first thing we need for this is, again, the formula of the compound, because it's written out for us. We have the molar mass. That's going to be helpful, but in this problem we have aluminum. And again, aluminum is not the most obvious one, but aluminum is right here on the periodic table. It has an S2P1 valence configuration. So when it forms ionic compounds, aluminum always forms +3 cations. Outside of the group 1 and group 2 cations, that's one that you should definitely remember, which is aluminum will always be +3. It loses all 3 of its valence electrons to make a cation. So in this compound here, we have aluminum 3+, and then perchlorate, we reviewed last time the formulas of those chloroxy type anions, which have chlorine oxygen, and perchlorate is the one that has the most oxygen, which is ClO4, and they all have a -1 charge. So the formula for this compound then to balance charges is going to be aluminum with 3 perchlorates to give the same positive and negative charge. So that's the formula of the compound, which has that molar mass. And then what we're looking for here is the molarity of just the perchlorate ions in the solution. So molarity, as we have to recall, is defined as, it's abbreviated as capital M, and it's defined as the moles of that substance divided by the volume of solution in liters. So in this problem here, the denominator is given to us pretty much directly, 125 milliliters of solution, which is 0.125 liters if we divide by 1,000. But then we need to get the moles of perchlorate to be able to finish out the calculation. So that's going to be a conversion that's somewhat similar to one we just did earlier, where we have a mass of our substance, 3.58 grams. We can convert to moles of that substance by using its molar mass. That's given to us in this problem, so we don't have to calculate it separately. So the molar mass of this compound is 325.32. That's script M. That's, again, kind of an archaic designation that you'd probably just see it as MW in your case. But it's 325.32 grams per mole. Now, this is the step that a lot of people forget, though. So a lot of people stop here, but we have to remember what these numbers mean. What we've now calculated is the moles of the total compound, aluminum perchlorate, that we've dissolved, but we just need the moles of perchlorate by itself. And so again, from that, there's this last step here that we have to do, where if we look at the formula of this compound, there's a subscript of 3 outside of perchlorate, so we're going to have 3 moles of perchlorate for every 1 mole of that compound that we dissolve. So this is the last number here, that last step here that many of you will forget to do or have forgotten to do in the past, so don't let it happen on the final. And so what that gives us then is 0.0330 moles of perchlorate. Because we're finding molarity of that ion individually, we need to make sure we have the correct number of moles of that ion when we dissolve it. And again, when 1 mole of this compound dissolves, it releases 3 moles of perchlorate, which is why we need that last step there. So now 0.0330 moles per 0.125 liters gives us a molarity of 0.264. So if you had forgotten that last step, you would have gotten a number that was 3 times smaller than this. That would represent the molarity of the whole compound, aluminum perchlorate. But to get the molarity of perchlorate when you dissolve it, it's going to be 3 times that, which is this number there. All right, I went through that kind of quickly, but we are just about out of time. So if there's any last questions, I can answer them now. If not, I'll be back here, not here, but in SEC 102 tomorrow, 2 p.m. to finish the last third of this review session. The last 2, there's, I think there's only 1 more for this section, which we'll pick up right where we left off. So we're going to start here tomorrow.